All right, guys, let's go through these here. For the sake of expediency, I will just do the talking so we can get straight into naming compounds today. Okay. So, idea of the atom was first proposed by whom? That would be Democritus. Okay. Democritus was the Greek thinker who said that everything was made of these tiny particles. Okay, but it was not well accepted because it didn't make sense. People were very comfortable and understood very well the workings of the four elements idea, okay, and so it was rejected at the time. Okay, for number 2, what elements did the Greeks believe all matter was made out of? Earth, air, fire, water. Those were the 4 elements. Okay, it made sense because they could see and kind of figure out, well, if I'm looking at mud, mud is a mixture of water and earth. Therefore, that makes perfect sense. And lava is, well, some parts earth and some parts fire and some parts water. So that makes sense too. Okay, steam, it's got some air and some water and some fire, and it just made sense. It was something they could understand and apply to their everyday life, so it was acceptable. Okay, the people in the Middle Ages who did a lot of work to develop chemistry were the alchemists. Okay, and their goals were to transmute common substances into gold, okay, or to make the elixir of immortality and things like that. Okay. Question number 4. In the 1700s, okay, was when Dalton came up with the atomic theory. Okay, and hopefully you summarized the 4 points into something along these lines. All matter is made of tiny, indivisible particles called atoms. Okay, atoms of one element are identical. Atoms of different elements are different. Okay, atoms can combine in simple whole number ratios. That part's got to be in point number 3 about the whole numbers. Okay, to form compounds. And fourthly, in a chemical reaction, atoms can be separated, joined, or rearranged, but not turned into the atoms of other elements. Okay, those are the 4 points of Dalton's atomic theory. Okay, question number 5. Looking at this theory now, what things do you know of that can prove some of his ideas wrong? Well, we can split the atom, at least some of them. Okay, so that would say that atoms are actually divisible if you have the right technology. Okay, and we know about isotopes. Okay, those versions of elements that have more neutrons than the normal amount, and thus their atoms are a bit different, even if they still exhibit a lot of the same properties. Okay, question number 6. Describe in your own words the models of the atom. Okay, give a brief explanation as to why each had been rejected or changed over the years. Do you think our current model may change, and why? So we started with the solid sphere. Okay, Dalton came up with that because it seemed to fit with the behavior of matter and reactions and physical changes and things like that. It was rejected because J.J. Thomson discovered that some chemical reactions produce electric currents, and the particle responsible for that are electrons. Dalton's solid sphere model did not account for that, so it was rejected and changed to the plum pudding model. Okay. Then we discovered protons, then we discovered neutrons, everything was up in the air for a while. Okay, some people believed still a solid sphere with positively charged things and negatively charged things on it. Other people thought about the nuclear model. Okay, and so Rutherford came along. He performed his gold foil experiment that proved the existence of the nucleus. Okay, and then from there, people argued about the arrangement of electrons. Okay, we had the Bohr model, but we generally settled on the de Broglie electron cloud model that explains and accounts for the fact that electrons can change energy levels, okay, and kind of jump around and make quantum leaps and things like that. Okay, could it change? Yep, it absolutely could. Okay, every time we think, oh, this is definitely the way things are, something comes along and proves us wrong. Okay, so that could definitely change. Okay, number 7, as our knowledge increased, we discovered the atom had smaller parts. Those parts are protons, which are positively charged in the nucleus. Neutrons, no charge in the nucleus. Electrons, negatively charged in the cloud. Okay, so if you got those things, that's generally what I would have been looking for, okay, for number 7. Okay, for number 8, if I have 1 cubic centimeter of lead and 1 cubic centimeter of carbon, the 1 cubic centimeter of lead is much heavier. Let's assume for right now that in that 1 cubic centimeter there are equal numbers of atoms. That would probably not be true, but let's say it is. Okay? If that's the case, why is the same number of lead atoms heavier than an equal number of carbon atoms? masses. Lead atoms have more particles in them, more protons, more neutrons, more electrons, thus they are heavier. Okay, number 9, nuclear reactors use atoms with very large nuclei, like uranium-237, okay, which has 237 particles in its nucleus. Why wouldn't they use smaller, less dangerous atoms like lithium, which has only 7 particles in its nucleus? Well, the answer is the bigger an atom gets, generally, the less stable it becomes, so it is easier to break. It's also a bigger target. Okay, trying to hit an atom of lithium compared to an atom of uranium would be like trying to make a shot from a mile away. Okay, you know, hitting like an apple versus hitting the broadside of a barn. Okay, it would be a lot easier to hit a uranium atom because it's just that much bigger. Also, bigger they are, the more energy they will release when they break. Okay, and so it just makes sense to use those. Now, just so we're aware kind of how this whole nuclear thing works. Okay, in a nuclear power plant, there are fuel rods. Okay, they're exactly like they sound. They're a metal rod with fuel pellets embedded on them. Okay, we want to make electricity with a nuclear power plant. We lower the fuel rod into the path of incoming particles, like free neutrons. Okay, and they just bombard these fuel pellets, which are just enriched uranium. Okay, when that happens, the atoms begin to split. When they split, okay, they get really hot. They release a ton of heat. Okay, and that evaporates water. The steam can turn a turbine, and that's how nuclear power is generated. If we need to generate more power, we lower more of the rod into the path of the neutrons, and so more fission occurs. If we want to decrease, or if the reactor is beginning to get too hot, then we pull the rods back out. Okay, or we flood the reactor with colder water, more cold water, in order to cool the system down. Okay, if you can't do that and all the water evaporates, what do you get? Yeah, you get a meltdown of some kind. Yeah. Okay, so that's definitely not what we would want. Okay, now this is generally a controlled reaction. We lower and raise the rods to control how much fission goes on, and as a result, it doesn't get out of control. In a nuclear bomb, that's exactly what we want, or whoever's setting it off wants. Generally, we don't want it, but okay, in a nuclear bomb, I'm showing you how to make a nuclear bomb, by the way, like really, really rudimentary. It's far more technical than what I'm about to show you. Okay, so what we have in a nuclear bomb is a chunk of fissionable material in the middle of a shaped charge. Okay, so basically a whole bunch of high explosive, like C4 or something like that. Okay, and we've got the fissionable material encased inside of it. It's focused, shaped, so that when it's detonated, the particles produced in the explosion will move inwards rapidly towards the fissionable material, and that will cause it to start splitting. And as it starts splitting, the pieces of it fly off and hit other atoms, which start them splitting. That causes a chain reaction that gets out of control really, really fast and causes the big mushroom cloud and destruction and all of that stuff. Okay, so it's actually one small explosion followed by one really big explosion, but they're so close together you never know the difference. Okay, but that's also why if you've ever watched like a video of an atomic bomb going off, why it seems to start kind of slow. There's like a flash, and then everything is kind of, it's building. It's a chain reaction. All right, does that make sense? Okay, so atoms are indivisible. We believed that for so long because, well, we couldn't prove otherwise. We couldn't split them ourselves, and then we discovered that sometimes atoms actually split on their own. Okay, Marie Curie, Henri Becquerel, scientists like that who studied for short periods of time, radioactive materials, discovered that, well, sort of their people who read their research after they died of cancer discovered, okay, that yes, some things actually break down and release radiation. Okay, Henri Becquerel's desk is actually in a museum in France, and it's encased behind lead glass, so you can see it, but you can't get close to it, because if you took a Geiger counter, one of those things that goes click, 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 click when you get near something radioactive, his desk is still radioactive because he had these special rocks that he studied. You know, the ore of uranium and plutonium and things like that. Okay, that's what he was studying, and he kept them in his desk, not knowing it was like sitting in an X-ray machine all day long, every day. Okay, like the guy probably went home and glowed in the dark. Okay? And that was kind of the same for anyone who was studying that stuff at that time, because they just didn't know any better. Radiation is invisible. They just were sick a lot, and yeah, because they were getting radiation poisoning at work all the time. All right. For number 11, from what you know of the structure of the atom, why do you think the atom stays intact? Why don't the electrons fly off? Well, electrons are negative, protons are positive, so they are attracted to each other, just like the Earth is attracted to the sun and the moon is attracted to the Earth. They move in an orbit that's stable, and they don't fly off. Okay? And then the same principle that makes glow-in-the-dark materials is used by plants. We actually talked about this the day I taught it. It has to do with solar radiation strikes the chlorophyll, and the electrons that are part of that chlorophyll molecule get excited. They move up to higher energy levels, and when they fall back down, that energy is what's used to break up the water and the carbon dioxide and make sugar in the process of photosynthesis. So it has to do with de Broglie's electron cloud model and the fact that electrons can jump from one level to another, and then when they fall back down, they release the energy they gained. Okay. All right, questions on any of those? Okay, keep those answers because they're what you're going to need to study for your quiz this week, which is going to be tomorrow, not Thursday, okay? Because we had a long weekend, we were supposed to have one today. I'm not going to be here Thursday, and I don't want my sub to have to give it to you, so it's going to be tomorrow. I've already said it, it's going to post at 3:20 today, okay? So you'll get the questions like what you're going to get, okay, on Wednesday, and you can check them out tonight and get them done. It won't take you very long, okay? It's going to be on this stuff, okay? These 12 questions. Okay, if I can get you guys to find lesson 2 in your notes package, that is what we'll go over next.